Imagine holding every book ever written, every photograph ever taken, every memory you've ever had, and watching them all disappear forever. Not just hidden, not just lost, but erased from existence itself, as if they never were. This isn't science fiction. This is what happens at the event horizon of a black hole. And in 1974, when Stephen Hawking discovered that black holes slowly evaporate and die, he revealed something that shattered the foundation of physics itself. Because according to the laws of quantum mechanics, information cannot be destroyed, ever. It's as fundamental to our universe as the speed of light. But black holes don't care about our laws. They devour information completely, leaving nothing behind. Because two of our most successful theories, quantum mechanics and general relativity, locked in mortal contradiction. Both cannot be right, both cannot be wrong. Yet here we stand, forced to choose between them. For 50 years, the greatest minds in physics have struggled with this paradox. What they've discovered along the way suggests something so strange, so utterly alien to our intuition, that it threatens to rewrite everything we thought we knew about reality itself. Today, we journey through evidence that challenges the very nature of space, time, and existence. Prepare yourselves. We begin. March 1974, Cambridge University. A young physicist named Stephen Hawking was about to announce something impossible. Black holes, those gravitational monsters from which nothing can escape, not even light itself, were dying. Slowly, gradually, they were evaporating away, leaking radiation into the cosmos until they exploded in a final flash of energy and ceased to exist. The announcement sent shockwaves through the physics community. Black holes weren't supposed to emit anything. That's what made them black. The very definition of a black hole required that anything crossing its event horizon was lost forever, trapped behind a one-way barrier in space-time from which no information could ever return. But Hawking had done the mathematics. When you carefully examined the quantum effects near the black hole's event horizon, something remarkable emerged. The intense gravitational field didn't just warp space, it tore at the quantum vacuum itself, creating pairs of particles from pure energy. Usually, these particle pairs would immediately annihilate each other. But at the event horizon, something different happened. Picture the event horizon, that invisible boundary around a black hole where gravity becomes so intense that escape velocity exceeds the speed of light. Now imagine quantum particles spontaneously appearing in pairs right at this boundary. One particle inside the horizon, one particle outside. The particle inside falls into the black hole. The particle outside escapes into space. To an observer far away, it looks like the black hole is radiating particles. But here's the crucial detail. This radiation carries away energy. And since Einstein taught us that energy and mass are equivalent, the black hole is losing mass. A stellar mass black hole, say 10 times the mass of our Sun, would emit this Hawking radiation at an incredibly cold temperature, about 1/10,000,000th of a degree above absolute zero. It would take 10 to the 67 years to evaporate completely, far longer than the current age of the universe. But the mathematics was clear. Given enough time, every black hole would shrink, accelerating as it got smaller and hotter, until it vanished in a burst of high-energy radiation. The implications, extraordinary. Black holes had temperature, they had entropy, they obeyed the laws of thermodynamics. They were not eternal prisons, but temporary storage systems with expiration dates. Yet within Hawking's beautiful discovery lurked something terrible, something that would haunt physics for the next 5 decades. The radiation escaping a black hole was thermal, completely random, containing no information about what had fallen in. It was like the heat from a fire. You couldn't reconstruct what had burned by measuring the temperature of the smoke. Think about what this means. Imagine throwing an encyclopedia into a black hole. Every letter, every word, every piece of information it contains, gone. Not just trapped inside, because eventually the black hole evaporates. Not encoded in the radiation, because Hawking radiation is completely random, simply deleted. This wasn't just philosophically troubling, it violated one of the most fundamental principles in quantum mechanics. In quantum mechanics, information is sacred. The technical term is unitarity, the principle that information about a quantum system is never lost, only transformed. You might scramble it, encrypt it, hide it in increasingly complex ways, but the information always exists somewhere. This isn't negotiable. It's built into the mathematical structure of quantum mechanics at the deepest possible level. If you allow information to be destroyed, the entire framework collapses. Probabilities stop adding up to 1. Cause and effect break down. The predictive power of physics evaporates. Yet here was general relativity, our best theory of gravity and spacetime, insisting that black holes could destroy information. And here was quantum mechanics, our best theory of matter and energy, insisting this was impossible. Both theories had been tested thousands of times. Both had passed every experimental challenge. Both were cornerstones of modern physics. Both made predictions accurate to 15 decimal places. Both could not be right. Hawking himself struggled with the implications. In 1976, he formalized the problem in a paper that would define a generation of physics research. If black holes destroyed information, he argued, then perhaps quantum mechanics needed modification. Perhaps information could be destroyed under extreme gravitational conditions. Other physicists recoiled in horror. John Preskill, a theoretical physicist at Caltech, insisted the opposite. Quantum mechanics was sanctimonious. If there was a paradox, general relativity must be incomplete. The battle lines were drawn. The black hole information paradox was born. But the evidence forces us to confront an uncomfortable possibility. Perhaps both are wrong. Perhaps reality itself works in ways so strange, so utterly alien to our intuition, that it threatens to rewrite everything we thought we knew about reality itself.
Before we dive deeper, we need to understand just how serious this crisis became. Because the information paradox isn't just about black holes, it's about the fundamental structure of reality. In 1973, just before Hawking's discovery, Jacob Bekenstein made a startling proposal. He calculated that a black hole's entropy, its disorder, its information content, should be proportional not to its volume, but to its surface area. Specifically, the entropy equals 1/4 of the event horizon's area measured in Planck units. For a black hole with the mass of our Sun, that's about 10 to the 77 bits of information, more information than exists in all the matter that collapsed to form it. This was bizarre. In ordinary physics, information scales with volume. A box twice as big holds twice as much information, but black holes don't work this way. They're like two-dimensional surfaces that somehow encode three-dimensional information. Scientists discovered something extraordinary. The Bekenstein-Hawking entropy formula suggested that all the information about a black hole was somehow stored on its surface, not in its interior. In 1993, Gerard Toft proposed something radical. What if this wasn't unique to black holes? What if all of three-dimensional space was actually information encoded on a two-dimensional boundary? Leonard Susskind developed this into the holographic principle. Just as a hologram projects three-dimensional images from a two-dimensional film, perhaps our entire universe is information encoded on a distant two-dimensional boundary. The mathematics suggested something profound. The maximum information that could be contained in any region of space was proportional to its surface area, not its volume. We appear to live in three dimensions, but perhaps we're really two-dimensional information projected into a 3D illusion. This sounds like science fiction, but it became one of the leading candidates for resolving the information paradox. Meanwhile, physicists exploring string theory, the attempt to unify quantum mechanics and gravity, found their own clues. In 1997, Juan Maldacena discovered a precise mathematical relationship between string theory in a five-dimensional space and quantum field theory on its four-dimensional boundary. The ADS-CFT correspondence, as it became known, provided the first concrete example of holography in action. More importantly, in this framework, information was preserved. What looked like information destruction from within the space was actually information preservation on the boundary. The calculations were exact. The correspondence was proven. For the first time, physicists had a working example of how information could escape a black hole. It was never truly inside to begin with. The information paradox represents just one piece of a much larger puzzle, because in 2012, physicists discovered that saving information might create an even worse problem. Ahmed Almeri, Donald Marolf, Joseph Polchinski, and James Sully, the AMPS collaboration, showed that if information escapes a black hole, the event horizon must be replaced by a firewall, a region of incredibly high-energy radiation that would incinerate anything trying to cross it. This directly contradicted general relativity's equivalence principle, which states that someone falling into a black hole shouldn't notice anything special at the event horizon. You should fall smoothly through, experiencing nothing unusual until tidal forces rip you apart near the singularity. The firewall paradox presented a trilemma. You could preserve 1. Information, 2. the equivalence principle, or 3. the laws of quantum mechanics. Choose any two, and the third must be sacrificed. Physics was in crisis. The resolution, when it began to emerge, came from an unexpected direction: quantum entanglement. Entanglement is quantum mechanics at its strangest. When two particles are entangled, measuring one instantly affects the other regardless of the distance between them. Einstein called it spooky action at a distance and never fully accepted it, but experiments have confirmed it thousands of times. In 2013, Juan Maldacena and Leonard Susskind proposed something audacious. What if entanglement and space-time geometry were actually just quantum entanglement viewed through the lens of gravity? They called it ER equals EPR, linking Einstein-Rosen bridges, wormholes, with Einstein-Podolsky-Rosen pairs, quantum entangled pairs. If true, it meant space-time itself was woven from quantum entanglement. The most remarkable discovery involves how this resolves the information paradox. In 1993, Don Page calculated what should happen to information as a black hole evaporates. Initially, no information escapes. The entropy of the radiation increases. But at halfway point of evaporation, something should change. Information should start escaping faster than it goes in. By the time the black hole disappears, all information should be recovered. Plot this on a graph. Entropy rises, reaches a peak, then falls back to zero. This is the Page curve, and it represents information preservation. But calculating this curve from first principles proved impossible for decades. The mathematics seem to require information to be both inside and outside the black hole simultaneously, a violation of quantum mechanics called the cloning paradox. Then, in 2019, everything changed. Jeff Pennington, Stephen Shenker, Douglas Stanford, and others made a stunning discovery using quantum extremal surfaces, a new way to calculate entropy in quantum gravity. They computed the page curve exactly. The calculations showed information beginning to leak out at precisely the halfway point of evaporation, exactly as Page predicted. Information was preserved. But here's what made it work. They had to include quantum corrections to space-time itself. The interior of the black hole wasn't actually separate from the exterior. They were quantum mechanically connected in ways that classical geometry couldn't capture. The event horizon wasn't a sharp boundary, but a fuzzy quantum region where interior and exterior overlapped. Information didn't escape through the horizon. It was never truly on one side or the other. These theoretical breakthroughs coincide with remarkable observational advances. In 2019, the Event Horizon Telescope captured the first image of a black hole in the galaxy M87. In 2022, they imaged Sagittarius A star, the supermassive black hole at the galaxy's center. While we can't directly observe Hawking radiation, it's far too faint. These observations confirm our models of black hole geometry to unprecedented precision. They show that general relativity works exactly as predicted at large scales. But the information paradox suggests that at the quantum level, in the microscopic structure of space-time near the horizon, reality operates according to rules we're only beginning to comprehend. The evidence extends beyond black holes into the realm of quantum gravity itself, suggesting that space and time are not fundamental but emergent properties of quantum entanglement. Let's step back and see the full picture emerging from 50 years of research. The evidence increasingly points toward a radical conclusion. We live in a holographic universe, not a simulation, that's different, but a reality where three-dimensional space is actually information encoded on a two-dimensional surface. Gerard Toft and Leonard Susskind originally proposed this to resolve the information paradox. But as physicists explored the implications, they realized it was far more than a solution to one problem. It was a complete reconceptualization of reality. In this framework, every region of space has a maximum information capacity, determined by its surface area. This is the Bekenstein bound, and it's not just true for black holes, it's true everywhere. Your room, your body, the Earth, the entire observable universe, all are fundamentally two-dimensional information projected into three dimensions. Leonard Susskind, now at Stanford University, has spent decades developing these ideas. He argues that black hole complementarity, the principle that information appears to an outside observer to remain on the horizon while appearing to fall through to an infalling observer, resolves the paradox without firewalls. Juan Maldacena at the Institute for Advanced Study has provided the mathematical proof that holography works through the ADS-CFT correspondence. His work shows that a complete quantum description of gravity can be equivalent to a non-gravitational theory on a lower dimensional boundary. Meanwhile, researchers like Daniel Harlow at MIT argue that the real lesson is quantum error correction. Just as computers use redundancy to protect information from corruption, space-time itself may use quantum error correction to preserve information across the event horizon. Stephen Hawking himself eventually conceded. In 2004, he admitted he'd been wrong about information destruction and paid off his bet with John Preskill, delivering an encyclopedia on baseball, the information from which, Hawking joked, Preskill could recover if he ever fell into a black hole. This forces us to reconsider fundamental assumptions about reality. If space-time is emergent from quantum entanglement, then space and time aren't fundamental aspects of nature. They're secondary properties, like temperature or pressure, useful descriptions of collective behavior, but not truly elementary. Causality itself might be emergent. The arrow of time, the distinction between past and future, could be consequences of entropy increase rather than fundamental features of physics. Some physicists go further. If information is truly preserved and if the universe is holographic, then in principle, every event that ever happened is encoded somewhere in the current state of the universe. The entire history of reality, from the Big Bang to this moment, exists as information that could theoretically be reconstructed. This raises profound questions about determinism, free will, and the nature of consciousness itself. We're entering an era where some of these ideas might become testable. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from colliding black holes in 2015. Future detectors like LISA, the Laser Interferometer Space Antenna, planned for the 2030s, will observe black hole mergers with exquisite precision. When black holes merge, they form a new black hole with an event horizon larger than the sum of the original horizons. Information theory predicts specific patterns in the gravitational waves emitted during merger. LISA might detect subtle deviations that reveal quantum effects at the horizon. The Event Horizon Telescope continues improving. Next-generation arrays might resolve structure near the event horizon at scales where quantum effects become important. While we can't image individual quantum fluctuations, statistical patterns in the shadow's edge could reveal quantum geometry. Recent breakthroughs suggest we might even detect Hawking radiation indirectly. In 2020, researchers created analog black holes in laboratory fluids and observed radiation consistent with Hawking's predictions. While not actual black holes, these experiments prove the mechanism works and suggest ways to test related phenomena. The information paradox has become the testing ground for theories of quantum gravity, the still undiscovered theory that unifies quantum mechanics and general relativity. String theory, where particles are vibrating strings in 10-dimensional space, has produced the most concrete progress through holography. But other approaches are converging on similar conclusions. Loop quantum mechanics, which proposes that space-time itself is quantized into discrete units, suggests information is preserved through quantum geometry of the event horizon. The horizon isn't smooth, but composed of discrete quantum states that encode information. Causal set theory, where space-time emerges from a discrete network of causal relationships, provides yet another framework where information preservation falls out naturally. What's remarkable is that these very different approaches all point towards the same conclusion. Information is preserved, space-time is emergent, and reality is fundamentally quantum. This naturally raises a question many find unsettling. If we live in a holographic universe where everything is information encoded on a boundary, are we living in a simulation? The answer is subtle. Holograms don't mean we're a computer program running on some alien machine. It means the mathematical structure of reality can be equivalently described as information on a boundary. But that boundary is part of our universe, not external to it. Think of it this way. A hologram isn't fake compared to the object it represents. It's a different encoding of the same information. Similarly, our holographic universe isn't less real than some hypothetical bulk reality. It's a complete description of everything that exists. However, the holographic principle does suggest that the complexity of the universe, the amount of information it contains, is finite.
The entire observable universe, with its 2 trillion galaxies and 10 to the 23 stars, contains approximately 10 to the 122 bits of information. Vast, but not infinite. Perhaps the most profound implication is this: we are made of quantum information. Your thoughts, your memories, your sense of self, all are patterns of information encoded in the quantum states of particles in your brain. And if information is never destroyed, then in some sense, everything that happens is permanently encoded in the structure of reality. Every thought you've had, every choice you've made, every moment of your existence, all preserved as quantum information in the holographic structure of space-time.
We've journeyed from Hawking's discovery through decades of theoretical struggle to recent breakthroughs. Now we must confront what all of this evidence actually means. The most profound implications emerge when we consider what holography tells us about the nature of existence itself. If space-time is emergent from quantum entanglement, then everything we perceive, the solidity of matter, the flow of time, the 3 dimensions of space, all are secondary phenomena arising from something more fundamental. We're like characters in a novel perceiving plot and causality, unaware that we're actually patterns of ink on pages. But here's where it gets strange. The pages in this analogy, the fundamental quantum information, don't exist in space or time. Space and time are what emerge from them. The fundamental layer of reality is something our brains literally cannot visualize, because visualization requires space. Recent work by Daniel Harlow, Patrick Hayden, and others suggest space-time itself might be a quantum error-correcting code. Just as computers use redundancy to preserve information despite errors, the structure of space-time might redundantly encode information across the horizon. This explains why local observers see information fall in, while distant observers see it encoded on the horizon. They're accessing different parts of an error-correcting code that contains the same information redundantly. But quantum error correction has a strange property. The code is more fundamental than the information it encodes. In other words, the structure of space-time, the error-correcting code, determines what patterns of information can exist within it. This suggests the laws of physics aren't arbitrary rules imposed on space-time. They're consequences of space-time's quantum information structure. Gravity, electromagnetism, the strong and weak nuclear forces, all emerge from the requirement that quantum information must be preserved. Yet even with all this progress, deep mysteries remain. The singularity at a black hole's center, where density becomes infinite and equations break down, still defies understanding. Quantum gravity should smooth out this singularity, but we don't yet know how. The cosmological information paradox poses similar questions about the entire universe. If the universe is accelerating its expansion due to dark energy, we're developing our own horizon, a cosmic event horizon, beyond which galaxies recede faster than light. Does the universe destroy information? Or is there some cosmic holographic boundary where everything is preserved? And perhaps most puzzling, if information from the interior of a black hole is actually encoded on its horizon, then for someone falling in, reality must be radically different than it appears. You'd think you were falling through empty space toward a central singularity, but the mathematics suggest you're actually hitting a dense layer of information at the horizon itself. Which perspective is real, or are both valid descriptions of the same underlying quantum reality? Based on current evidence, several futures seem possible. In one scenario, we develop a complete theory of quantum gravity within the next few decades. String theory, loop quantum gravity, or some synthesis reveals the exact mechanism of information preservation. We learn to calculate black hole evaporation precisely, and perhaps even harness quantum gravitational effects for technology. In another, the information paradox leads us to even stranger revelations. Perhaps consciousness itself is a quantum phenomenon that interacts with space-time geometry. Perhaps the observer plays a more fundamental role in reality than we've imagined. Or perhaps we discover that our entire universe is just one hologram among many. The bulk space-time that our universe is holographically projected from might contain countless other holographic surfaces, each encoding its own universe with its own laws of physics. The evidence suggests we're approaching a transformation in human understanding as profound as the Copernican revolution or the development of quantum mechanics. We began with a paradox. Black holes seemed to destroy information, violating quantum mechanics' most sacred principle. We've journeyed through 50 decades of theoretical struggle, brilliant insights, and recent breakthroughs that finally point toward resolution. The evidence now suggests our universe is holographic, space-time is emergent from quantum entanglement, and information is preserved through quantum error correction at the event horizon. Black holes don't destroy information, they scramble it in increasingly complex ways before encoding it in their radiation. But the deeper revelation is what this tells us about reality itself. We don't live in space and time, we are space and time. Patterns of quantum information whose interactions create the illusion of three-dimensional reality and temporal flow. The current scientific consensus recognizes that while we haven't fully solved quantum gravity, the information paradox has guided us toward genuine insights. Holography is now a central principle in theoretical physics. The connection between entanglement and geometry is firmly established, and the preservation of information is non-negotiable. We've learned that black holes aren't cosmic garbage disposals, but quantum information processors. We've learned that space-time itself is an emergent phenomenon, and we've learned that reality at its deepest level operates according to principles still alien to human intuition. Yet how much do we truly understand? We've mapped the borders of the territory, but the interior remains mysterious. The exact mechanism of information escape still eludes us. The quantum structure of space-time remains unknown. The relationship between consciousness and quantum mechanics remains unresolved. Stephen Hawking once said, "The fact that we human beings, who ourselves are mere collections of fundamental particles of nature, have been able to come this close to an understanding of the laws governing us and our universe is a great triumph." We stand at the edge of discovery, looking into the quantum void where space and time dissolve into pure information. What we found there challenges everything we thought we knew, and yet it's also profoundly beautiful. A universe where information is sacred, where nothing is truly lost, where reality itself emerges from the simplest possible principle. Quantum mechanics must be preserved. The paradox that threatened to break physics has instead pointed us toward a deeper understanding of existence itself. The universe is vast, the mysteries are endless, the journey continues. Imagine holding every book ever written, every photograph ever taken, every memory you've ever had, every thought that ever crossed your mind, and watching them all disappear forever. Not just hidden, not just lost somewhere you can't reach, but erased from existence itself, deleted from the universe as if they never were. This isn't science fiction. This isn't a thought experiment. This is what happens at the event horizon of a black hole, according to our best understanding of physics. And in 1974, when a young Stephen Hawking discovered that black holes slowly evaporate and die, leaking radiation into the cosmos until they vanish in a final burst of energy, he revealed something that shattered the foundation of modern physics itself. Because according to the ironclad laws of quantum mechanics, laws tested in billions of experiments over a century, information cannot be destroyed, ever. Not hidden, not transformed beyond recognition, but fundamentally preserved in the quantum structure of reality. It's as fundamental to our universe as the speed of light, as inviolable as the conservation of energy. But black holes don't care about our laws. They devour stars, gas, light, and matter. They swallow information completely, leaving nothing behind but gravity and radiation that contains no trace of what fell in. The two of our most successful theories, quantum mechanics and general relativity, locked in mortal contradiction. Both have been tested thousands of times. Both have passed every experimental challenge with flying colors. Both make predictions accurate to 15 decimal places. Both are cornerstones of our understanding of reality. Both cannot be right. Both cannot be wrong. Yet here we stand, forced to choose between them, like a parent forced to choose between children. For 50 years, the greatest minds in physics have struggled with this paradox. Nobel laureates have built careers on it. Entire fields of theoretical physics have emerged from attempts to resolve it. What they've discovered along the way suggests something so strange, so utterly alien to human intuition, that it threatens to rewrite everything we thought we knew about space, time, matter, and existence itself. The evidence suggests we don't live in the universe, we are the universe. Patterns of quantum information playing out on a two-dimensional cosmic screen, projecting the illusion of three-dimensional reality, like a hologram more elaborate than anything human technology could create. Today, we journey through evidence that challenges the very nature of reality. Prepare yourselves. Nothing will look the same when we're done. We begin. Cambridge University, England. Spring rain patters against Gothic windows. In a small office, a young physicist hunches over pages of equations, his hands cramped from hours of calculation. At 32 years old, Stephen Hawking has already made his mark studying the origins of the universe. But what he's discovered now will eclipse everything that came before. For months, he's been examining what happens to quantum fields near the event horizon of a black hole, that invisible boundary where gravity becomes so intense that escape velocity exceeds light speed. The mathematics are extraordinarily difficult, requiring a synthesis of quantum field theory and general relativity that has never been attempted before. And now, staring at the final equation, Hawking sees something impossible. Black holes emit radiation. They glow. They leak energy into space. They die. The announcement sends shockwaves through the physics community. Within days, the news reaches Princeton, Caltech, Moscow, and Tokyo. Senior physicists check and recheck the calculations. The mathematics are elegant, beautiful, and absolutely rigorous. They're absolutely wrong. They have to be wrong, because black holes, by definition, don't emit anything. That's what makes them black. The very essence of a black hole is that anything crossing its event horizon is lost forever, trapped behind a one-way barrier in space-time from which no information can ever return. But Hawking has done the mathematics correctly. When you carefully examine quantum effects near a black hole's event horizon, something remarkable emerges: the quantum vacuum. To understand what Hawking discovered, we need to understand something strange about empty space. What we call a vacuum, perfect emptiness, isn't empty at all. According to quantum mechanics, the universe operates on a cosmic energy loan system. The Heisenberg uncertainty principle states that you can't simultaneously know both the energy of a system and the exact time you're measuring it. This isn't a limitation of our instruments, it's a fundamental property of reality. This uncertainty means that for incredibly brief moments, empty space can spontaneously create pairs of particles from pure energy, a particle and its antimatter twin. These virtual particles exist for such a short time that they don't violate energy conservation. They pop into existence, exist for perhaps 10 to the minus 21 seconds, then annihilate each other and vanish. This happens everywhere, constantly. Right now, in the space between your eyes and this screen, quadrillions of particle pairs are flickering in and out of existence every second. You don't notice because they cancel out immediately. But near a black hole, something different happens. Picture the event horizon, that invisible sphere around a black hole where gravity becomes so intense that not even light can escape. The radius of this sphere, the Schwarzschild radius, depends on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would be about 3 kilometers in radius. For the supermassive black hole at the center of our galaxy, 4 million times more massive, the event horizon is about 12 million kilometers across, larger than the orbit of Mercury. Now imagine quantum particles spontaneously appearing in pairs right at this boundary, one particle inside the horizon, one outside. Normally, these particles would immediately find each other and annihilate. But here, gravity intervenes. The particle inside the horizon is trapped by gravity. It cannot escape, cannot reach its partner. It falls inward toward the singularity. The particle outside the horizon, meanwhile, is free. To an observer watching from a safe distance, it looks like the black hole has emitted a particle, radiation streaming away from a place where nothing should escape. But here's the crucial detail. This radiation carries away energy. And since Einstein taught us that energy and mass are equivalent, that's what E equals mc squared means, the black hole is losing mass. Each particle that escapes represents a tiny decrease in the black hole's mass. Hawking calculated the exact temperature of this radiation. For a stellar mass black hole, say 10 times the mass of our Sun, the temperature would be about 1/10,000,000th of a degree above absolute zero. That's 10 to the minus 7 Kelvin, colder than the cosmic microwave background that permeates all of space. For such a black hole to evaporate completely would take approximately 10 to the 67 years. That's a 1 followed by 67 zeros. To put that in perspective, the universe is currently 13.8 billion years old, or about 10 to the 10 years. The evaporation time is trillions of trillions of trillions of trillions of times longer than the current age of the universe. But smaller black holes evaporate faster and hotter. A black hole with the mass of Mount Everest would have an event horizon the size of a nanometer and would evaporate in seconds, exploding with the energy of millions of nuclear weapons. A primordial black hole formed in the Big Bang with the mass of a large asteroid would be evaporating right now, ending its life in a burst of high-energy gamma rays. The mathematics was clear and beautiful. Given enough time, given an almost incomprehensible amount of time, every black hole in the universe would shrink, accelerating as it got smaller and hotter, until it vanished in a final flash of high-energy radiation. The implications. The announcement was revolutionary. Black holes weren't eternal. They weren't perfect cosmic prisons. They had temperature. They had entropy. They obeyed the laws of thermodynamics. They were dynamic objects with life cycles, born from collapsing stars, living for eons, and eventually dying in spectacular fashion. Physicists immediately recognized the significance. Jacob Bekenstein, who had proposed that black holes have entropy in 1973, saw his controversial ideas vindicated.
The Hawking radiation gave black holes a concrete temperature, confirming Bekenstein's entropy formula. But within Hawking's beautiful discovery lurked something terrible, something that would haunt physics for the next 5 decades and counting. Let's look more carefully at what Hawking actually calculated. The radiation escaping a black hole isn't like light reflecting off a mirror carrying an image of what's inside.
This means information can be scrambled, encrypted, hidden in increasingly complex correlations between particles, but it always exists somewhere. You might lose track of it practically, but in principle, with perfect knowledge and infinite computational power, you could always recover it. This isn't negotiable. It's not a convenience or an approximation. It's built into the mathematical structure of quantum mechanics at the deepest possible level. If you allow information to be destroyed, if you allow non-unitary evolution, the entire framework collapses. Here's why. In quantum mechanics, probabilities must add up to 1. If an electron can be in state A or B, the probability of A plus the probability of B must equal 100%. If information can be destroyed, probabilities stop adding up correctly. The predictive power of quantum mechanics evaporates. Cause and effect break down. Yet here was general relativity, our best theory of gravity and space-time, insisting that black holes could destroy information completely. And here was quantum mechanics, our best theory of matter and energy at the smallest scales, insisting this was impossible. Both theories had been tested thousands of times. Both had passed every experimental challenge. Both were cornerstones of modern physics. General relativity had predicted the perihelion precession of Mercury, explained gravitational lensing, predicted gravitational waves, later detected, and described the expansion of the universe. Its predictions were accurate to better than 1 part in a trillion. Quantum mechanics had explained atomic spectra, predicted antimatter, enabled the transistor and laser, and made predictions verified to 15 decimal places. The magnetic moment of the electron, for instance, is predicted by quantum electrodynamics to agree with measurement to 1 part in a trillion. Both could not be right. Both could not be wrong. Hawking himself struggled deeply with the implications. For 2 years after his initial discovery, he worked to find some escape, some way to preserve information in the Hawking radiation. He couldn't find one. In 1976, he published a paper that would define a generation of physics research. If black holes destroyed information, he argued, then perhaps quantum mechanics needed modification. Perhaps under extreme gravitational conditions, conditions we've never tested in laboratories, the sacred principle of unitarity breaks down. Maybe, Hawking suggested, the wave function doesn't always evolve unitarily. Maybe nature has a collapse mechanism that destroys information when gravity becomes strong enough. Maybe there's a fundamental limit to information preservation. The physics community erupted in debate. Some sided with Hawking, willing to contemplate modifying quantum mechanics in extreme conditions. Others recoiled in horror at the suggestion. John Preskill, a theoretical physicist at Caltech, became one of the most vocal opponents of information destruction. In 1997, he made a famous bet with Hawking and Kip Thorne. When the information paradox was resolved, the loser would provide the winner with an encyclopedia from which information can be recovered at will. Preskill insisted that quantum mechanics was sacrosanct. If there was a paradox, it meant general relativity was incomplete. There must be quantum corrections to Einstein's theory that preserved information, even if we hadn't discovered them. Leonard Susskind at Stanford took an even stronger position. He argued that black holes must be fundamentally quantum objects that couldn't be correctly described by classical general relativity alone. Information had to be preserved somehow, and finding out how would require a quantum theory of gravity. Gerard 't Hooft in the Netherlands proposed radical solutions involving modifications to quantum mechanics at microscopic scales beyond current experimental reach. The battle lines were drawn. Careers would be built and destroyed over this question. Friendships would strain. The black hole information paradox had become the defining problem in theoretical physics. But the evidence forces us to confront an uncomfortable possibility. Perhaps both theories are wrong. Perhaps reality itself works in ways so strange, so counterintuitive, that we need an entirely new framework to understand it. Perhaps we've been asking the wrong questions all along. Before Hawking's discovery, another physicist had noticed something deeply strange about black holes. Jacob Bekenstein, working as a graduate student at Princeton in the early 1970s, had been thinking about what happens when you throw a hot cup of coffee into a black hole. The coffee has entropy, disorder in thermodynamic terms. The second law of thermodynamics states that the total entropy of a closed system always increases. But when the coffee crosses the event horizon, its entropy seems to disappear from our universe entirely. Does this violate the second law? Bekenstein proposed a radical solution. Black holes themselves must have entropy, and using thermodynamic arguments combined with quantum mechanics and general relativity, he calculated what that entropy should be. The result was shocking. A black hole's entropy, Bekenstein proposed, was proportional not to its volume, as you'd expect for normal objects, but to the area of its event horizon. Specifically, S equals Ka over 4L squared, where S is entropy, K is Boltzmann's constant, A is the area of the event horizon, and L is the Planck length, the smallest meaningful length in physics, about 10 to the minus 35 meters. Let's calculate this for a real black hole. Take a stellar mass black hole with 10 times the mass of our Sun. Its event horizon has a radius of about 30 kilometers, giving it a surface area of about 10 to the 13 square meters. Plug this into Bekenstein's formula, and you get an entropy of about 10 to the 77th. That's a 1 followed by 77 zeros. In information theory terms, that's 10 to the 77th bits. To put that in perspective, all the data humanity has ever created, every book ever written, every photo ever taken, every video ever recorded, every website, every email, every thought ever posted on social media, totals perhaps 10 to the 23 bytes, or about 10 to the 24 bits. A single stellar mass black hole can store more information than a trillion copies of all human data combined. But here's what made Bekenstein's formula bizarre. This entropy is proportional to surface area, not volume. In ordinary physics, information scales with volume. A box twice as big can hold twice as many books. A hard drive with twice the volume can store twice as much data. The amount of information in a region of space should depend on how many particles it contains, which depends on its volume. But black holes don't work this way. Double a black hole's mass and you double its radius, which increases its surface area by a factor of 4 and its volume by a factor of 8. Yet the entropy only quadruples, scaling with area. It's as if all the information about a black hole is somehow stored on its surface, not in its interior. As if a three-dimensional object were actually a two-dimensional surface that only appears three-dimensional. When Hawking discovered his radiation formula, it perfectly confirmed Bekenstein's entropy. The temperature of Hawking radiation combined with thermodynamic laws gave exactly the entropy formula Bekenstein had proposed, entropy proportional to horizon area.
This wasn't a coincidence. This was physics telling us something profound about the nature of information and reality. In 1993, Gerard 't Hooft was wrestling with the information paradox when he had a radical insight. What if the area scaling of black hole entropy wasn't unique to black holes? What if this was a fundamental property of all of space-time? He proposed something extraordinary. Perhaps the maximum information that could be contained in any region of space, any region, not just black holes, was proportional to the area of its boundary, not its volume. Leonard Susskind, working independently, developed the same idea. They called it the holographic principle, inspired by holographic photography, where a two-dimensional film encodes three-dimensional images. The principle states all the information contained in a region of space can be represented by information on the boundary of that region. A region twice as big can contain at most 4 times as much information, doubled in two-dimensional spaces, not 8 times doubled in three-dimensional spaces. Think about what this means. Take any region of space, this room, the Earth.
In 1997, a young physicist named Juan Maldacena made what many considered the most important discovery in theoretical physics in decades. Working at Harvard, Maldacena was exploring string theory, the attempt to describe all particles as vibrating strings in 10-dimensional space. He discovered a precise mathematical relationship between two completely different theories. On one side, a theory of gravity in a 5-dimensional space with a particular geometric structure called anti-de Sitter space, or ADS. On the other side, a quantum field theory without gravity living on the 4-dimensional boundary of that space, a conformal field theory, or CFT. The ADS-CFT correspondence, as it became known, showed these theories are exactly equivalent. Everything that happens in the gravitational 5-dimensional interior has a perfect mathematical translation to the non-gravitational 4-dimensional boundary. It was the first concrete, mathematically precise example of holography in action. Within months, physicists around the world recognized the significance. Here was proof that holography wasn't just speculation, it was a demonstrable mathematical fact, at least in this particular case. More importantly for the information paradox, in the ADS-CFT correspondence, information is manifestly preserved. What looks like information destruction from inside a space, say matter falling into a black hole in the interior, is actually just information preservation on the boundary, described by the conformal field theory where unitarity is guaranteed. The calculations were exact. The correspondence was proven. You could calculate something in the gravitational theory, translate to the boundary theory, verify information conservation, and then translate back. For the first time, physicists had a working example of how information could escape a black hole. It was never truly inside to begin with. The interior and boundary were just two different descriptions, two different languages for the same underlying reality. String theory itself provides a framework where quantum mechanics and gravity can coexist. In string theory, particles aren't point-like objects, but tiny vibrating strings. Different vibration patterns correspond to different particles. One pattern gives an electron, another a photon, another a quark. String theory requires 6 extra spatial dimensions beyond the 3 we observe. These extra dimensions are compactified, rolled up so small we can't perceive them, like an ant walking on a power line perceiving 1 dimension but living in 3. The theory makes testable predictions about particle physics and cosmology, though most are beyond current experimental reach. But more importantly, it provides a consistent mathematical framework where quantum field theory and general relativity emerge as approximations. Within string theory, black holes are smooth quantum objects called fuzzballs, tangles of vibrating strings with no true event horizon or singularity at the quantum level. Information is preserved because it's encoded in the quantum state of the fuzzball, and Hawking radiation carries away this information as the fuzzball evaporates. By the early 2000s, multiple lines of evidence pointed toward the same conclusion. First, black hole thermodynamics. The Bekenstein-Hawking entropy formula, confirmed by countless calculations, showed that information scaled with area. Second, the holographic principle, a general framework suggesting all of space-time had this property, not just black holes. Third, ADS-CFT, a concrete mathematical proof that holography works and information is preserved in at least one example. Fourth, string theory itself, a framework where black holes are quantum objects without true singularities, naturally preserving information. Fifth, quantum mechanics itself, the unbroken track record of unitarity in every experiment ever performed. The evidence was accumulating. Information must be preserved. The question was, how? But in 2012, just when physicists thought they were converging on a solution, disaster struck. 4 physicists, Ahmed Almiri, Donald Marloff, Joseph Polchinski, and James Sully, the AMPS collaboration, published a paper that would throw the field into crisis once again. They showed that if information escapes a black hole via Hawking radiation, quantum mechanics forces a terrible conclusion. The event horizon must be replaced by a firewall, an incredibly high-energy radiation that would instantly incinerate anything trying to cross it. Here's why. Hawking radiation must be entangled with the black hole's interior to carry away information. But early radiation is also entangled with late radiation, and quantum mechanics forbids a particle from being maximally entangled with 2 different systems simultaneously. The only way to break this contradiction is to sever the entanglement between interior and exterior right at the horizon. But severing quantum entanglement releases enormous energy. The event horizon becomes a wall of fire. The firewall paradox presented physics with an impossible choice. You could preserve information conservation, the equivalence principle, nothing special at the horizon, quantum mechanics no cloning theorem, no copying quantum states. Choose any 2, and the third must be sacrificed. It was like being told you could keep your job or your family, but not both. The equivalence principle is central to general relativity. It states that someone falling freely under gravity experiences no gravitational force. They're in inertial motion, like floating in space. An astronaut falling into a black hole shouldn't notice anything special when crossing the event horizon. They should fall smoothly through, experiencing nothing unusual until tidal forces rip them apart deep in the interior, near the singularity. But the firewall says, no, you burn up instantly at the horizon. Physics was in crisis, again. The resolution, when it began to emerge in 2013, came from thinking about the relationship between quantum entanglement and space-time geometry itself. Juan Maldacena and Leonard Susskind proposed something audacious. What if quantum entanglement and geometric connection were the same thing? What if the smooth connection of space-time was actually just quantum entanglement viewed through the lens of gravity? They called it ER equals EPR, linking Einstein-Rosen bridges, or wormholes, with Einstein-Podolsky-Rosen pairs, or entangled particles. The idea was radical. When 2 particles are entangled, they're connected by a tiny wormhole, a geometric bridge through space-time.
We can't use this connection to send information faster than light because we can't control what quantum measurements produce. But the geometric connection is real, manifesting as correlation between measurement outcomes. If this is true, then space-time itself is woven from quantum entanglement. The smoothness of space isn't fundamental. It emerges from countless microscopic quantum connections. Entanglement as space-time. This idea revolutionized how physicists thought about the information paradox. If space-time emerges from entanglement, then the rigid distinction between inside and outside a black hole breaks down at the quantum level. The event horizon isn't a sharp boundary, but a fuzzy quantum region where interior and exterior are entangled in complex ways. An observer falling in sees one description of reality. They fall smoothly through. An external observer sees another description. They see the information encoded on the horizon. But these are just two perspectives on the same quantum reality. In 1993, Don Page had calculated what should happen to information as a black hole evaporates, assuming information is conserved. Initially, as the black hole emits Hawking radiation, no information escapes. The entropy of the radiation increases as expected for thermal radiation. But at the halfway point of evaporation, when the black hole has lost half its initial mass, something should change. Information should start escaping faster than new thermal entropy is generated. The entropy of the radiation should reach a maximum, then decrease. Plot this on a graph. Entropy rises, reaches a peak at the halfway point, then falls back to zero. This is the Page curve, and it represents perfect information preservation while appearing to respect thermodynamics. The problem was that calculating this curve from first principles proved impossible for decades. The mathematics seemed to require information to be both inside and outside the black holes simultaneously.
In 2019, a group of physicists, including Jeff Pennington at Stanford, Ahmed Almeri and Netta Engelhardt at Princeton, and Stephen Schenker and Douglas Stanford, published a series of papers that finally calculated the Page curve from first principles. They used a new technique called quantum extremal surfaces, a generalization of how we calculate entropy in quantum gravity. The key insight was that when calculating the entropy of Hawking radiation, you need to include quantum corrections to the geometry of space-time itself. In classical general relativity, space has a definite geometry. The event horizon is a definite surface. Interior and exterior are clearly separated. But in quantum gravity, geometry itself becomes fuzzy and uncertain. The event horizon isn't a sharp boundary but a quantum superposition of different possible boundaries. And when you calculate entropy correctly, accounting for these quantum fluctuations, something remarkable happens. Here's what they found. Early in the evaporation, when the black hole is large, the classical calculation is correct. The entropy of the Hawking radiation grows steadily as thermal radiation pours out. Information appears to be lost. But at the Page time, roughly the halfway point of evaporation, a quantum transition occurs. The calculation suddenly prefers a different quantum extremal surface that extends through the black hole's interior, connecting the radiation to degrees of freedom inside. After this transition, the entropy of the radiation stops growing and begins to decrease. Information that seemed lost inside the black hole is now escaping into the radiation. By the time the black hole completely evaporates, the entropy returns to zero. All information is recovered. The Page curve emerges naturally from the mathematics. But here's what made this resolution work. They had to include quantum corrections to space-time itself. The interior of the black hole isn't actually separate from the exterior in the way classical geometry suggests. At the quantum level, interior and exterior are connected,
entangled in ways that classical geometry cannot capture. The event horizon isn't a sharp boundary, but a quantum region where the distinction between inside and outside blurs. Information doesn't escape through the horizon in the classical sense. Rather, the quantum state describing the black hole and its radiation is fundamentally non-local. Information exists in quantum correlations that span both the apparent interior and the outgoing radiation. The calculation proved information is preserved, vindicating quantum mechanics. But it required abandoning our classical intuitions about space and time being fundamental. The papers created immediate excitement in the theoretical physics community. Within weeks, hundreds of physicists were working on extensions and applications. The techniques opened doors to calculations that had seemed impossible for decades. Stephen Hawking himself had unfortunately passed away in 2018, just 1 year before the resolution emerged. But in 2004, he'd already conceded his position, admitting he'd been wrong about information destruction. He paid off his bet with John Preskill, delivering an encyclopedia on baseball, the information from which, Hawking joked, Preskill could recover if he ever fell into a black hole. Leonard Susskind, who had fought for decades to preserve quantum mechanics, called the 2019 papers the most important development in the black hole information paradox since Hawking's original discovery. John Preskill noted that while we still don't have a complete picture of how information escapes, the page curve calculation proved it must escape, providing a roadmap for future work. The page curve tells us information is preserved, and even when it starts escaping, but many mysteries remain. How exactly does information encoded in the subtle quantum state of Hawking radiation? The radiation appears thermal to any practical measurement, yet somehow contains detailed information about what fell in. What does an observer falling into a black hole actually experience? Do they encounter a firewall, or do they fall smoothly through while quantum mechanics plays tricks with information behind their back? What is the quantum structure of spacetime near the horizon? The calculations prove quantum geometry is crucial, but we still don't have a complete description of what spacetime really looks like at the Planck scale. And most profoundly, what does this tell us about the nature of space and time themselves? Let's step back and see what 50 years of struggle have revealed. Multiple independent lines of reasoning from black hole thermodynamics to string theory to the recent page curve calculations all point towards the same revolutionary conclusion. We live in a holographic universe. Not a simulation, that's a different concept, but a reality where three-dimensional space and everything in it are actually information encoded on a two-dimensional boundary projected to create the illusion of an extra dimension. This isn't metaphorical, it's a precise mathematical statement about how information is structured in our universe. The evidence is overwhelming. First, black hole entropy scales with area, not volume, confirmed by countless independent calculations. Second, the AHTP correspondence generalizes this to all of spacetime, setting fundamental limits on information density. Third, the ADS-CFT correspondence proves holography works mathematically in at least one concrete example. Fourth, string theory and quantum gravity calculations consistently show that gravity in higher dimensional spaces is equivalent to non-gravitational theories in lower dimensions. Fifth, the page curve calculation requires quantum geometry where interior and exterior are fundamentally connected, consistent with holographic information storage on the boundary. Sixth, quantum entanglement itself seems to generate geometric connections, suggesting space emerges from quantum information. Every pathway leads to the same destination. Three-dimensional space is emergent, not fundamental.
Imagine a hologram, those shimmery stickers you might see on credit cards. Shine light on it and you see a three-dimensional image floating in space. You can move your head and see different angles. The image has depth, volume, and structure. But it's not really three-dimensional. All the information creating that 3D image is encoded in two-dimensional interference patterns on the hologram's surface. The third dimension is an illusion, a very convincing illusion, but an illusion. Now scale this up to the universe. Everything you see, stars, galaxies, planets, your own body, appears three-dimensional. You can move in three independent directions. Objects have volume and depth. But according to holography, all of this is information encoded on a two-dimensional boundary incredibly far away, perhaps at the edge of the observable universe, perhaps on some abstract quantum boundary. The three-dimensional world you experience is that information projected into apparent 3D space. Where is this boundary? This raises an obvious question. Where is the holographic boundary? Where is the screen encoding our reality? The answer depends on which holographic scenario you're considering. In ADS-CFT, the boundary is at spatial infinity, infinitely far away in a particular type of curved spacetime. For our actual universe, which appears to be expanding and filled with dark energy, the situation is more subtle. Some physicists propose the boundary is our cosmic horizon, the limit of the observable universe, currently about 46 billion light-years away. Information about everything within our observable universe is encoded on this cosmic horizon. Others suggest the boundary is more abstract, not located anywhere in physical space, but representing the maximum information capacity of space at every point. The mathematics works in various scenarios, but the physical interpretation remains an active area of research. Why haven't we noticed? If we're living in a hologram, why don't we notice? Why does space seem so obviously three-dimensional? The answer is that holography doesn't mean we're fake or that our experiences are illusions in the everyday sense. The holographic description and the 3D description are equivalent. They're two equally valid ways of describing the same reality. It's like asking whether water is really H2O molecules or really a continuous liquid. At the molecular level, it's discrete particles. At human scales, it's a smooth liquid. Both descriptions are correct for their respective scales. Similarly, at human scales, space is three-dimensional. We move through it, build houses in it, fly spacecraft through it. But at the fundamental quantum level, the information content suggests a two-dimensional structure with an emergent third dimension.